Okay, so let's continue. So remember last time I explained this Peery map in Calabi-Yau at the co-chain level, and basically we discussed the following. This is my Peery map. It looks like T 1 minus E mu over T mapped to the big space. And I explained, we explored basically the geometry of the image of this Peery map as a formal Lagrange submanifold. And this guy is the graph. We can write down basically the generating function of this Lagrangian. And using this string equation, Dirichlet equation, we figured out that this one has a rather explicit formula which illustrates its connection with topological gravity. And roughly speaking, that's the formula. And this is represents intersection number on the modular space of rational curves. Okay. And basically, the way we figure this out is to study the geometry of this Lagrangian submanifold. We basically figure out a bunch of Hamiltonian vector fields preserving this Lagrangian submanifold, and we write down the corresponding Hamilton-Jacobi equation. And this allows us to do some calculations. Now, today I want to explain the additional structure. This is a structure that allows us to pass to finite dimensional model to write down the corresponding invariants. And it's about this differential Q. And I showed you before that this linear operator Q acting on this space, viewed as a vector field, is tangent to this Lagrangian submanifold. So basically, we can do something similar to what we have done last time. Last time we explored this bosonic even symmetry, like a Virasoro symmetry. And now this operator is odd. So it's cohomological vector field. And I want to explain to you what's the corresponding geometry of this odd symmetry. And you can write down some kind of odd version of Hamilton-Jacobi equation. And that's going to be this object. This is the classical mass equation. So roughly speaking, this Q preserve this symplectic form as well. And then we can write down the corresponding quadratic Hamiltonian function. And let me say HQ. We will calculate it later. But this function is odd, basically. So because this one is odd, this even symplectic form is odd. But anyway, this similar versions of Hamilton-Jacobi equation still holds. So this one restricted to the Lagrangian is still 0. So we'll try to explore this equation a little bit. And to explain what's happening in this setup, so recall this Q has the following expression, like d bar plus t.
Refer to that this space is a dry space, so there will be an odd tangent space.
This odd is like this operator is odd. So this operator is odd. Degree 1. Yeah, that's all I mean. And but if you think about this linear map as a vector field, this one squares 0. So this homology degree of this one is 1. This is degree 1. This is degree 1. This is degree 2. This is degree minus 1. Whole thing is degree 1. Yeah. And Q squared equals 0. So this is what usually people call a cohomological vector field. But this vector field, no matter what, they're still compatible with the symplectic form. So it's a Hamiltonian. But because it's infinite dimensional, it's a little bit more subtle. I will try to explain to you what's happening. But intuitively, this is still Hamiltonian. You can write down the corresponding quadratic Hamiltonian function. That's odd function. It's odd function because this is even. But this equation still holds.
So d bar itself does not do self-omega.
This one is compatible. Yeah, this one preserved.
Everybody is self.
Yeah, it preserves. Yes.
So you have a loss of function.
Yes. Okay. Now remember, like some of the key properties is the following. Like if you try to illustrate how this vector field or this linear operator acts on the space, you see, like it preserves half of the data. But if you apply this one to the negative orders, this is not preserved. I mean, it will have both components. This implies that the quadratic Hamiltonian has a special type. And then let's try to figure this out. To avoid a little bit technical discussion on some kind of generalized functions, so I will explain a toy model, and hopefully this toy model will illustrate the answer in a straightforward way. So let me explain this toy model. This toy model will also help us to understand how to quantize the theory. Okay, so toy model, I really mean a finite dimensional situation. So this is like infinite dimensional, but let's work on finite dimensional model. And let's consider, for example, just to almost the same data, but now let me choose a different notation. Let's call this V omega Q. This is like a DG symplectic space. And I want this one to be even symplectic. Let's say just zero symplectic for simplicity. So this omega is like, let's say zero symplectic. It can be also even symplectic. And so this one particularly implies like this it has degree 0, and you can write down the corresponding. So because it's finite dimensional, you can view this one as a element of wedge 2. We do. That's the school symmetric pairing. Or you can write down the corresponding Poisson kernel, and this is going to be an element in wedge 2, V. Okay, so this is the symplectic pairing. This is the corresponding inverse matrix. This Poisson tensor. And now Q is compatible with omega. It's school symmetric. With respect to omega, they're compatible. So our previous example, like V is going to be S of X. This is infinite dimensional, but let's work on the finite dimensional situation. And I will illustrate how to work with the infinite dimensional case later. Okay, now here, similar to this situation, let's assume the following. We have a splitting.
So Q is the what? Q is a vector field or something?
It's a linear map. It's a DG space. So VQ is a chain complex.
Okay.
Yeah, this is differential represents the DG data. So the DG and the symplectic, they're compatible. And now then we have actually splitting. Similar to here, so you're gonna write this one as like V equals V plus, direct sum V minus. Just like the finite dimensional case is a little bit simpler to explain. So both of this one, plus minus, are Lagrangian subspace, linear Lagrangian subspace. The same situation here. And we also require like Q preserves part of the data. Just the same situation. And Q applied to minus. It may not be preserved, but let's write in such a way.
When you say zero symplectic, just a degree 1 will pair with degree minus.
Yes. Yes, literally degree 0 element here. Yeah. And this splitting also allows us to write the whole thing. Identify my V as the cotangent bundle of the V plus. This is the place where we use zero symplectic. And let's denote the corresponding projection to the V plus to be pi plus. Okay, that's the data we're going to use. Now this information basically the same thing as to what we have observed on here. And now I want to explain to you this the corresponding odd Hamilton-Jacobi equation. Okay. I'm going to erase this part. And yes, I'll just complete it parallel. Okay, so let's look at the corresponding Poisson kernel. And we know like this kernel in the beginning like lies in here, and this is this simple pair this plus and minus. So this one actually lies in this object. Actually, it's, these two components are skew symmetric of each other. So it's really like in this object. So it pairs V plus with V minus, V plus. So its inverse is the same thing, like lies in this object. So these two components are really different. And to illustrate the corresponding Hamiltonian function, and we can consider the following object. This object is really the one due to this Hamiltonian function. Let's consider Q tensor 1 applied to this Poisson kernel. The Poisson kernel has degree 0. This one has degree 1. And now you look at where this one actually lies. So you see, like this is like a Q applied to the first component. So if you apply to the first component, you look at this one. It still is an element here. And now you look at how it acts on the second component. Applied to V minus, there's something which is still lies in V minus, but there's something which basically break the symmetry and will jump into V plus. So it's really an element here. That's where this object lies in. And then let's look at, let's denote this component by P. And explicitly, P equals the projection of this object to the plus plus component. And later we will see this object plays a role of propagator in this B model. That's why I use the notation like symbol P. And from this description, this P measures the failure of the compatibility of the splitting. So this P equals 0 if and only if this splitting is compatible. It's a splitting of a chain complex. Now here's the proposition. Now it's purely linear algebra. First of all, like because my symplectic form is degree 0, the P has degree 1, and it's a degree 1 element. And when I say this is not only degree 1, but also like this is symmetric in these two pieces. Basically, it has dual to like function, like Hamiltonian function. I will say this in a minute. It's a symmetric element of this object, and this one is also Q compatible. So it means like apply Q to this object is 0 because it's a tensor.
Because Q is still symmetric or something?
Q is still symmetric, then this one is symmetric, yes. Yeah. And P basically is Q closed. And let's do a quick proof. I mean, illustrate the basic idea. So this will use the fact that this omega is skew symmetric, as Conan mentioned, and also the fact that Q is compatible with omega. So this compatibility means the following: like Q tensor 1 plus 1 tensor Q applied to omega inverse is 0. So it's like Q closed, this object. This is the compatibility. And then with this equation, you see like if you switch these two, 1 and Q and 1, if you switch these two, it's going to be remain the same structure. But if you switch these two components, you get a minus sign. So if then you put the other, put the stuff to the other side. So this implies, and this one is skew symmetric. Then it implies the following: like if you only look at the first component, apply this to this one, and then you switch both. This one become this one, and this one become a minus sign. You put this plus to the other side, the minus sign canceled out, and this implies the following: implies that Q tensor 1 applied to omega inverse is actually a symmetric object. That's just a very simple calculation. And then if you look at the components, this particular projection, this is also symmetric. And that's the end of the proof, roughly speaking. Now let me tell you, like this is nothing but actually the dual description of the Hamiltonian function associated to Q. So let me just quickly say this.
This P is
Part of the Hamiltonian function. I can write it down. Yeah. So geometrically, so what's already happening is the following: like we know this is like a Q tensor 1 applied to omega inverse. Just we mentioned this is an element of symmetric 2 tensor. And now using this symplectic form, we can basically identify V with U. That's the symplectic form. And then under this identification, this is a map to symmetric 2 of the V star. And then this object mapped to a quadratic function on the space. This is precisely the Hamiltonian function. So this is a quadratic Hamiltonian. Of the vector field. By the way, this is nothing. This is nothing but the other way of writing this, like contracting Q with omega, something like that. This is just written in a different way, but this is the same thing as saying you contract this omega with the contract this vector field with the two form omega, and you get a one form that's right down the corresponding Hamiltonian function. That's it. And the condition, you see, like the, but we know like this object contains, like for example, this is an element of let me say here. So HQ, original object, as I mentioned, it lies in V plus tensor V minus direct sum V minus tensor V plus. This is the original part we're preserving the splitting, but also the part coming from the failure. That's the P component. And then if you turn this one into this function, you see like it's mapped to V plus to V minus do and things like that. So we see like the Hamiltonian function is really an element of like this becomes V minus star. Do this is dual space, and the V plus do, and similar here. And the important object is the last component. It mapped to this component like sim2 V minus do. And sometimes we write like, because this is our base manifold, this is a cotangent bundle. So this is like a position and the momentum. And we can write this component like this Hamiltonian function like as like x and c in this component plus something like a momentum squared term. Something like that. This is quadratic in the momentum with this expression tells the linear part preserving the splitting. And now just think about what's the corresponding Hamilton-Jacobi equation. Every momentum becomes a derivative of the generating function. We restrict it to Lagrangian. So it just becomes a first order differential operator and composed with this one. This is nothing but a linear transformation. This one will be quadratic in this generating function. So let's write it down. And now I think I want to keep this picture a little bit. I draw it later. So to illustrate precisely what's happening, so let's define the following notion. And this notion will be important later when we describe the quantum theory. Now this P is an element in this symmetric 2 tensor. So you can view this one as like a second order differential operator with constant coefficient. So denote the corresponding linear differential operator just like partial P. This is second order differential operator applied to say a degree n polynomial. You end up with like degree n minus 2 polynomial. just by taking two derivatives. Or in terms of like symbols, like we can write this one algebraically, which are going to be useful for discussing the quantum theory. So this is nothing but by contracting with this Poisson kernel. Think about this one as like a differential operator. Let's say, suppose I denote this partial p applied to some polynomial function on plus. Then when you evaluate, it's like, think about this one as like a pairing between tensors. So if you evaluate this one on, like say, A1, etc., AM minus 2. So that's the pairing between like dual tensor and the tensor. And you simply just insert this object, phi P tensor, A1, etc. All this AI is an element of V plus. And this sign comes from the fact that the P has degree 1.
So is there a natural setting in finite dimensional that appear somewhere?
It's top. It's finite. Let me say it's a linear algebra. So
Yeah, but was this occurring in like usual systematic geometry?
I don't know. I need this one. Basically, I essentially need this infinite dimensional version of this. But yeah, but this is basically linear algebra. Yeah. And then you see, like this is an order 1, but this is a degree 1 second order differential operator. Okay, this does appear. Let me say this is like B-wave operator. So it like, looks like a divergence operator with respect to Calabi-Yau. That's a finite dimensional model. So you remember the operator, like this del operator on polyvector field. That's an example of this. Yeah.
And the V plus and V minus
So V plus. Which one is
V plus, yeah.
V plus is just the whole thing. It's like a, let me say if you apply this one to this really the whole thing is like a shifted cotangent of something. Yeah. In that example.
V minus?
No, V plus. V minus is the dual of this guy. Literally the cotangent of this whole the bigger one. So you see, like this is like second order. So that's why it's called a B-wave operator. So we define the so-called associate. So this is not a derivation, and you can look at the failure of this one being a derivation, as what we did for this divergence operator before on Calabi-Yau. So the failure is give rise to a bracket, and this is the so-called B-wave bracket in this case. So I didn't call the corresponding bracket before B-wave bracket. This is essentially the Schouten bracket on this polyvector field. I'm gonna call this one B-wave bracket because that's the B-wave bracket which leads to the quantization story. So I'm gonna denote like FG a B-wave bracket with respect to this Poisson kernel by the failure of this one being a derivation. This is my definition. The same formula as before, and it satisfied a completely the same set of relations, like against the Haber relations and things like that. Okay, so by exactly the same calculation, now we can show the following. Let me just say in words. Proposition. And look at like functions on V plus, and you look at your So let's say this is symmetric function tensors of the dual, and you have remember like Q actually preserve Q plus V plus. So induce a differential by duality to a differential here. So this is induced differential on functions. And then you have a second order operator given by this Poisson tensor. You have this partial P. And then you have this induced BB bracket describing the failure of this one being a derivation. This object is an example of like a differential Gansen-Hilbert BB algebra. And this is a very canonical way to produce such an object. So the proof is also automatic, so I won't say. Just one small thing I want to mention is like, because like Q is compatible with P, and this will imply that this differential Q is commutes in the graded sense with this operator. So that's the compatibility of this differential with the BV operator. And the other stuff just follows easily.
So does the Q depending on the choice of V minus? P depending on the choice of V minus?
Q, so Q is, in practice, VQ is a starting point. It's a chain complex.
Yeah, but that is the Q on the...
Yes.
So the Q is the same.
So Q is the same Q.
So
But if you change V minus, you change P.
change.
Yeah, yes.
And then these are isomorphic algebra?
If you change it slowly,
Slowly.
yes. Okay. Now let me show you the metric. No, it's not metric. It's just a somehow standard symplectic geometry. So now assume we have Lagrange submanifold. We have a Lagrange submanifold. And inside V, and now I have identified V with the cotangent bond of V plus by the choice of V minus. This is my L. And suppose this Lagrangian is described by the generating function I naught. So suppose like I naught is the generating function. So means like this L basically is the graph of D I naught. Then the proposition is the following. And Q is tangent to L. So this differential is tangent to this Lagrange submanifold, and if and only if Q applied to I naught. So I naught now is a function. If I view this I naught function is an element here, and then you have this bracket. Equals 0. This is called the classical mass equation.
So I'm not depending on V minus.
Yes.
On this case.
Yeah, yes, that's right. Yeah. The proof is literally just it's a simple calculus. It's just by thinking, by looking, and simple calculus. So nothing more complicated. So you basically, it's an is basically odd Hamilton-Jacobi equation. So this is the same thing as saying that this one is tangent to the Lagrangian, same thing as saying that it's Hamiltonian function restrict to this Lagrangian. It's constant, but in this case it's odd, it's 0. And then you look at what this Hamiltonian function look like. You see like the first term, we restrict this one to Hamiltonian. You basically replace this momentum by this derivative of this I naught. And if you think about it a little bit, like the first term, just tell like take the derivation for x, and for some linear compilation of x, the same is as q. The second term is a bilinear object, and if you just restrict this one to this object, and you think about it, like what's the coefficient here? This coefficient is precisely inserting this p. And just by thinking, by simple calculus, you find this equation.
Can V minus, we will tangent, Q tangent to V minus?
Which one?
V minus.
V minus to what?
Can Q tangent to V minus?
Q tangent to V minus. Then it's going to be, the p is going to be 0. Yeah, so there's no this term anymore. So this p is basically the failure of Q tangent to V minus. Preserving V minus. Yeah.
But you still have the first one.
You have this equation, but it's just like this one is 0. It's Q closed. Nothing else.
Yeah, but I still is delta function. I still is not a function.
Oh, if you work with that's right. I mean, you can still have a Lagrangian, and yeah, if you have one direction along this line, you're saying you might have to force you to have to shrink.
Or the
Yeah,
whole L is there.
maybe. Yeah, I think you're right. Yeah. You have to force you to have this delta function behavior at one direction pointing to this area.
Whether that can happen?
I don't know. I mean, maybe it's a very degenerate situation of this one. Maybe I have no idea, but
You can just use another
yeah.
track that.
Yeah.
Move the L to V minus.
Mm-hmm. Yeah, you see, like when let's say when this Lagrangian somehow, in that case, you cannot write this one as a graph of this object, right? When you have that direction, you have to change to another polarization to write this. Yeah, but somehow this is really the one way to express this fact. I mean, this is more dramatic, more intrinsic. This is just one way. If you want to write down some functions to express this fact, that's the thing, right? Maybe you choose the wrong thing to write it, but this is more dramatic. Now,
EGBV algebra data as a choice of V minus.
yes, it is. Yeah, it is true. Yes. You change V minus, you change the whole thing, and that's basically the origin of holomorphic normal equation. Holomorphic normal equation is the change of the optic filtration. It's like tau bar. You have tau and tau bar. Yeah, tau is the Hodge filtration. Tau bar is the splitting. So that really happens in practice. Now I want to tell you actually another way of looking at this. I mean, basically, you see, now classical mass equation can be written in a different way. Denote. You know, this is like whenever you write down classical mass equation, the same thing as writing down some kind of nonlinear cohomological vector field on the space. And that corresponding cohomological vector field, let's call this one delta. The leading term is Q, and plus another term is like Hamiltonian vector field. Not Hamiltonian vector field, but it's a bracketing, UV bracket with this function.
So all this translation of the V plus is always satisfied this?
Or which one?
Translation. Parallel, if L is parallel to V plus, is Q tangent to that?
If you do
Just parallel.
up a little bit,
Yeah.
I doubt.
That's not true.
I doubt. Yeah. And then also, even if you shoot a little bit, it's gonna be if it's tangent, then it's gonna be valued in some central term as well. It's not 0. It's like I say this is 0 just because it passed orange at some point, but like Hamilton-Jacobian equation says, like this one restricted Lagrangian is a constant. Literally, that's what it said. But you can shift the constant. Now, you think about this operation as a vector field, a derivation, acts on functions on V plus. So it's really a vector field. It's a nonlinear vector field. This classical mass equation says that this Q squared equals 0. And geometrically, this is very simple to understand. It literally is the following object. And so you see, like, you have a vector field here, which is tangent to the Lagrange submanifold. Then you see, like, there's a projection map. Because it's a tangent, geometrically, you can push forward this vector field to downstairs. So literally, another way of expressing this Hamilton-Jacobi equation is the following, like geometrically. This vector field basically is the push forward of the vector field Q, restrict to this Lagrangian. And you know Q squared equals 0, then it must be true that delta squared equals 0. So that's another way to explain this classical mass equation. Is that clear? Yes, at some point. This is a different way to look at the same object. And essentially the same, yeah.
So I just wonder, in the trivial case where V is 2 dimension, V plus V minus a 1 dimension, what are the possible?
You need a one odd dimension and one coding odd dimension. So it's like you need this odd vector field. So
you need both.
you need an odd variable. You probably can write down some simple model for this. Like you need one even variable, one odd variable.
Okay, V plus V even and V minus V odd.
No, they are even symplectic. So this V plus have to contain both even odd, and V minus contain both even odd.
So the simplest example is R4.
Well, R2, yeah, R2/2, yes, like, yeah.
These are all, okay, so these are all, it's like a supersymmetry Q. I mean, it's like a,
Yes. Maybe they can be used to study like Cauchy algebra, things like that. I've never thought about it, how to implement this in this data, but in principle, yes. And let me quickly say what's happening for the real case, because we work with infinite dimensional situation. So, but once we understand,
Q squared equal to 0, right?
yeah.
Will Q squared equal to some translation make any sense?
Q square, what kind of
Supersymmetry, right? Q squared.
you can have like Q square equals the lead derivative or something. That makes sense. Yeah. You can do that. You can do equivalent localization.
Okay.
Yeah. Now let's go back to a B model on Calabi-Yau. It's a little bit more subtle, but the structure is almost the same. So let me just say in words about what's the final answer, and I hope it's not strange to see the result. So now we have to have this kind of splitting, and then we know like Q basically break the splitting by looking at how it acts on S minus part. The same situation. Now, because it's like infinite dimensional, it's a little bit subtle. So the symplectic pairing is again even symplectic. Its omega can be written as something like, it's like a trace pairing, and with some kind of residues. Something like that. And this is not issue. This is basically discrete. This is some kind of issue because trace here basically is like integration. So this looks like integration. You integrate on the manifold. So that's a little bit trouble, but not hard to imagine. Like the inverse of the pairing by integration is precisely delta function. So you can write down this inverse literally as the delta function, or more precisely, it's given by this delta diagonal t to the k tensor minus t to the minus k minus 1. So his delta is the delta function distribution. It's distributional element of Pauli tensor Pauli. So this is basically delta function. But as far as classical theory is concerned, delta function is actually okay. But at the quantum level, we're running into trouble. I will tell you what's happening. So, but it's clear like delta function is the inverse of integration pairing. So when you write down the integral kernel for the identity operator, that's the delta function. But anyway, just let me write down. This one is basically the integral kernel for this identity operator applied to polyvector fields. Now let's write down, just basically pretend we do the same thing as we have done for finite dimensional situation. And we write down a corresponding P. Oh, by the way, I say this P is a propagator, it's not true. I will explain. This is not a propagator, it's a BV kernel. And I will explain propagator later. This P, I use a little bit bad notation. Hopefully I can correct it later. This notation is a little bit misleading, but since I have written it down and since it's recorded, so I probably should keep this notation at this moment. But anyway. So now we need to apply this Q tensor 1 to this Poisson kernel, and then look at the projection to the plus part. And then if you look at this a little bit, my Q is del bar plus T del. And then you look at this expression here. This operator only breaks this splitting a little bit by the component of like T to the order of minus 1. So you see like this P is a failure of Q preserving the splitting. And the Q basically fails a little bit by applying this one to T to the order 1 part. because if all -2, then this is still okay, right? Apply to here, it goes to the negative part a little bit. This a little bit is very important actually. It means like the theory is a degenerate theory, degenerate BV theory. This is a highly unusual situation in physics. But anyway, let's write it down. You see, like, so this is the part which break, and break only a little bit. And you write it down, this is only del applied tensor 1 applied to the delta distribution. So this is like distributional section element, again, in this poly, tensor poly. It's a singular along the diagonal. Okay. Now, but let's just keep going. So now, the question is like, can we make sense of this equation a little bit for this distributional kernel? Well,
So this looks like not a little bit, right? This is pretty big.
which one?
Is that the p supposed to be very close to be 0, right? Because it's delta function, so it's 0 almost everywhere except.
Yeah, exact along diagonal. Yeah. So you see, like, I want to say, so, as far as this function or functional is local, then the bracket still makes sense because this is like a delta function. As far as this is like an integration, then, well, you have two integrations. You insert the delta function. This is well defined on local functionals. And so, precisely, given any kind of local functional, a local functional I on this S plus. Now S plus is very big. It's like a polyvector field with descendant I write element here by mu0 plus t mu1 plus etc. And for I is a function of like all these components like a mu case. And local means like this is given by some integration of something. And for example, our BCOA action is local because it is a trace map integrated on the Calabi-Yau manifold. Then you can do the same thing, like once you have something local, you can do some kind of variation calculus. Like assume, like say, suppose you do variation, like it's like calculate a d of something. And if you do variation, this is local, you can always write this variation in this case by the following, like sum of k's, because it's like many components. And this, now, for our case of polyvector fields, integration is implemented by this trace. So this is basic integration. And you can always write this variation as the following form, like delta mu k, delta I, delta mu k. That's the way you define this variation. This is a functional of variation calculus. And then I'm gonna keep this page. We're gonna use this one in the infinite dimensional case. And yes. Now, similarly, we can define the BV bracket. Let's call this one bracket 0. For local functional, suppose I have two functionals, I can just define the same object, I1, I2 bracket, by basically insert this P kernel into this formula. But what this formula precisely says, it looks like a Pij partial I partial j something. Now, in the infinite dimensional case, you want to implement this formula in a more precise way. Then, this derivation is implemented by this variation. And then the kernel, just the integral kernel for this del operator. So this is not hard to imagine. Like this is the definition of this one is given by trace and delta I1, delta. And you see, like this only component in t to the power of 0. There's no higher term. So this kernel, this element only lies pick up this component, nothing else. So you only calculate the variation for the mu naught component. And then you insert this p operator. It's the same thing as inserting this del operation, and then do this bilinear variation. That's the definition of this BB bracket. And this is well defined because this variation gives you something local, and then this is an element of this is some kind of element in the polyvector field, and you take the divergence operator, and then you pair with another polyvector field and take trace. This is still integration. So this is still local functional, still local. So this operation basically is well defined. Now, just by copying basically what's been proved here, you can write down the theorem. Not hard to imagine, like the BCU action. We call it I0x before. Satisfied the following classical mass equations, like Q applied to I naught x plus 1/2 bracket equals 0. It's the classical mass equation for the B model. And this is the infinite dimensional version of the Hamilton-Jacobi equation. And you can actually check explicitly why this holds. I mean, just by suppose you don't know this Hamilton-Jacobi equation, you just throw into this definition and calculate it. You can find this calculation on my thesis. You find like this equation has the same thing as the data encoding genus 0 topological recursive relation. Like roughly speaking, you calculate some kind of a descendant of k1 plus 1 and k2 and k3 and blah 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 equals something like tau 1, and you insert a tau 0 and tau 2, tau 3, and something else. So there's just some kind of equation like called topological recursive relation. If you just explicitly calculate what this equation says, you find this equation basically is a consequence of this genus 0 topological recursive relation. So
this is, but you're doing not a world-ship perspective, right?
No, it's not.
So this topological recursive is when you do final thing?
No, literally it's the equation for this tau intersection number on the moduli space of the operational curves. You can say it's coincidence.
There's a world-ship perspective.
Yeah, but it just observed this is the same object. So this is an incidence of like target description, but it's sort of, you're right, it's sort of mysterious, which is true. And so far we don't have an understanding about what's the corresponding higher genus recursion relation related to quantum mass equation. That's not known yet, even like genus 1 or 2. Yeah. So I think I will make a break here. So after break, I will explain to you the issue about the quantization. Yeah.